Good evening, ladies and gentlemen. Tonight, I'm going to walk you through 5 application problems using the Bernoulli equation. If you find this helpful, I'm going to kindly ask that you please subscribe. It's a free and simple act for you that would help me tremendously. If you have any questions for any of these problems or for future fluids problems, please put them in the comments. And with that, let's dive into the first problem. Application problem number 1. When an airplane is flying at 200 miles per hour at 5,000 feet altitude in a standard atmosphere, the air velocity at a certain point on the wing is 300 miles per hour relative to the airplane. Part A. What suction pressure is developed on the wing at that point? And part B. What is the pressure at the leading edge, a stagnation point on the wing? All right, so the first thing we're going to notice here is that the 5,000 feet altitude is pretty useless. So we just want to point that out because we have density already given as a function. And so we can just totally disregard that. The next thing we want to notice is that everything is in feet. So we want to convert out of miles per hour and into feet. So we're going to do part A down here. And the first step we're going to do is we're going to convert V1 from 200 miles per hour out into feet per second, which turns out to be 293.3. Otherwise, we'd have some big problems with our units. And then V3, we're going to do the same thing, 300 miles per hour into, coincidentally, 440 flat feet per second. So, with that, we are now, again, using the Bernoulli equation, which will take us from, in this case, point 1 to point 3. And that does follow a streamline. We can easily get there. This does not violate any of the rules or assumptions that the Bernoulli equation makes. And so this is totally viable. So we will have P1 plus, we don't really have to account for height here. So we're just going to have P1 plus 1/2 rho V1 squared is equal to P3 plus 1/2 rho V3 squared. And here we want to notice that this is at atmospheric pressure, and we're going to measure this with respect to atmospheric pressure, and so P1 will just turn to 0. And with that, we actually have our expression for P3. This problem is probably going to be the most simple of them all. And so bear with me as we ramp up in difficulty. So we're going to factor out some of these things. And that's our expression. Taking it right over here. P3 is equal to 1/2 rho. We're going to plug in our unit for density. So 2.048 times 10 to the negative 3 slugs per feet cubed. And then this will be multiplied by the difference in squares between our velocities, which is 293.3 feet per second, squared minus, I'm going to have to write it down on this bottom line here, 440 feet per second squared. Sorry, not feet per second squared. Feet per second, and then the whole quantity is squared. And so we could put brackets around here just to make that real obvious. All right. And if we solve this out, P3 gets resolved to negative 110.16 pounds per feet squared. All right. And that's part A. Beautiful. Part B, we're going to do right up here. This one's also very simple, very direct. And so part B, we'll be going from point 1 to point 2, which is a stagnation point. And because it's a stagnation point, point 2 has no velocity. So we will have P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. Here we know V2 is 0. We know P1 is 0 because it's atmospheric. And then P2 is just equal to 1/2 rho V1 squared. Then we're going to plug in our painfully long expression where we've got 2.048 times 10 to the negative 3 slugs per feet cubed. We'll make that one quantity times V1, which is 293.3 feet per second, quantity squared. And P2 is now equal to 88.09. Don't forget our units. It is pounds per feet squared. And that's the first problem, easiest of the bunch. Application problem 2. A pedostatic tube is used to measure the velocity of helium in a pipe. The temperature and pressure are 40 Fahrenheit and 25 psi absolute. The water manometer connected to the pedostatic tube indicates a reading of 20 inches. Determine the helium velocity. Is it reasonable to consider the flow as incompressible? So, first thing to unpack is the height we're talking about, this guy up here, is 20 inches. So this is 20 inches. And then as we're reading this manometer, keep in mind this is gaseous, this is helium, and the density of water is so much greater than helium. We don't need to account for this when we go back and do our pressure balance. But before we begin, there's a few things we ought to do. First of all, we ought to convert some of these things into more standardized units. PSI kind of sucks. So we're going to convert that from PSI absolute to PSF, and we're going to get 3600 absolute pounds per square foot absolute. And then the temperature we're also going to convert from 40 Fahrenheit to Rankine. And that will give us nearly 500, but not quite. And then that's Rankine. And then the height, we also want to convert height from 20 inches into 1.6667 feet. These are values we want to have on hand because most of the units we'll be dealing with may be in absolute temperature, or it'll probably be in feet in some capacity. So the first thing we want to do is we want to go from point 1 to point 2. The reason we put point 1 right here in level with point 2 is so we don't have to take into account the density of helium. It wouldn't be much, but if this was water, for example, we don't know this distance, we don't know this height, so we don't want to put it up there. And the static pressure here is the same as the static pressure up in this column. So that's why we put it here. And we are just going to write out our classic Bernoulli equation. So we'll have P1 plus 1/2 rho V1 squared plus rho G Z1. And all that is equal to P2 plus 1/2 rho V2 squared plus rho G Z2. And keep in mind, Z1 is equal to Z2. Z is measuring the elevation from some datum, which we're just going to call 0 right here because they're in plane. And so because of that, because they're equal, these will turn to 0. And then something else we can notice is that point 2 is a stagnation point because that's literally just what is going on. This is a pedostatic tube. This is blocking the flow. And so V2 is going to be 0. And so we are looking for V1. That's what we're solving for. And so we are going to re-express this so that we can isolate for V1 a little easier. So this will be P2 minus P1. Notably, P2 minus P1 is essentially this height in head of water. So we'll get back to that. But V is equal to 2P2 minus P1 all over rho Square root the whole thing. So that's our key equation. We're going to need to come back to that. I'm going to start on a new page here because this is going to get a little messy. But the density of helium, so actually, if we go back, this density is of helium. This fluid is helium. We only touch water for this pressure balance. And we don't know the density of helium. We need to go figure that out, which is going to be difficult. So we need to use the ideal gas law. We can typically, always assume that this is an ideal gas if it's flowing at 40 Fahrenheit and 25 psi. That's warm enough to keep it from being liquid. It's essentially superheated. So you just need to know that helium applies as an ideal gas here. Really, also, this is the only way to get density, so that's kind of a hint. So the ideal gas law breaks down into being rho r t. Oh my gosh, that's so big. Let's make this a little smaller because we are going to use most of this page. Rho r t is equal to p. Now this r is specific to helium. Helium, ideal gas constant. So that this is not just a generic r. That's why we don't have m in here or whatever. And so then we're just going to isolate for rho. And we will get rho is equal to p over RT, where P is the pressure where the helium is existing, so 25 psia, and T is temperature in absolute, so Kelvin or Rankine. In this case, we're dealing with Rankine. So we're going to do 3600, because again, we need to put this in standardized units. PSF, it's kind of assumed that it's absolute. And then the R value, you would probably need to look up on some table or in your book, but I have it here, 1.242 times 10 to the 4. Not to the negative 4, just to the 4th. And then the units of that are feet per pound per slugs, or feet pounds per slugs, Rankine. And then temperature is 499.67 Rankine. And when we evaluate that, rho is equal to 5.80 times 10 to the negative 4 slugs per feet cubed. So that's our density. We need that. The next thing we also need, if we're going to take a flashback here. Oh, that does not. Okay. We need our delta P's. All right. And so we're going to resolve that right now as well. So P2 minus P1 is equal to, again, the head of 20 inches in water. So this is going to be H2O because that is our manometer fluid. And we're not resolving the density or the specific gravity of helium in there because it's just so insignificant. And so the gamma of water, or specific gravity, is 62.4 pounds per foot cubed. And then we'll multiply that by H in feet, which is 1.667 feet. And so this P2 minus P1 is equal to 104 exactly pounds per foot squared. And with that, we can go back and resolve our velocity. So I'm going to plug in all the values now. I'm not going to redraw the equation. V1, it's going to be a nice and big expression. We're going to have 2 times 104 pounds per foot squared all over 5.80 times 10 to the negative 4 slugs per foot cubed. And so we resolve that. V1 is equal to 5, or rather, let's put an arrow there, 598.85 feet per second squared. This is not the end of the problem, though. It asked, can we assume that this is incompressible? In order to do that, we need the Mach number. And so I'm going to kind of draw a line down the edge of this page to show that we are starting a new calculation. And this has to do with Mach number. Mach number is equal to velocity over c, where c is the speed of sound. And the equation for c is equal to square root kappa times RT. Again, this R is not universal. This is the helium ideal gas constant, and T is in absolute. And this kappa is the isentropic ratio. And you will need to look that up in your textbook on some table, something like that. It may be given on a test. If it's not, you got to go hunt that down in the back of your book. So we're going to resolve C first before we do anything else. C, and we're going to need a lot of space, is really just a plug and chug. Kappa for this is 1.66 for helium. So I'll save you the effort. But then we're just going to do 1.242 for the R times 10 to the positive fourth. Again, not the negative fourth, to the positive fourth. Feet per pound slugs Rankine. All right, now we're going to have to squeeze this last guy in. 499.67 Rankine. All right. And then C is equal to 3209.6 feet per second. And with that, we can take both of these. We can bring this down and our C, and then solve. Well, actually, we're also going to need this velocity. So Mach number is equal to 598.85 feet per second all over 3209.6 feet per second. And then the Mach number comes out to be 0.187, which is less than 0.3. And 0.3 is the threshold for compressibility, really. Incompressible. Because it meets this criteria, because it is less than 0.3. And that is the answer. We've got this plus this velocity. We now have solved it all and explained our reasoning. Application problem 3. Water flows from the faucet on the first floor of the building shown in the figure below with a maximum velocity of 16 feet per second. For steady and viscid flow, determine the maximum water velocity from the basement faucet and from the faucet on the second floor. Assume each floor is 12 feet tall. So, the first floor faucet is this guy over here. The second floor faucet is here labeled V1 in red. And then the basement faucet is here labeled V2 in the very bottom in red. We have a few dimensions given. Here, the shaded in regions are solid. The not shaded in regions are representing pipe with water flowing through them. And we're going to use the Bernoulli equation to resolve this. So the points we're going to select, first of all, we're going to have a point right up here in the free stream, in the free jet. This will be point 1. We'll have point 2 down here in the basement, point 2, and then we're going to put point 3 in the known jet velocity. So the first thing we want to do is we want to decide what we're solving for. And so I'm going to have us solve for v2 first of all, v2. And then we're just going to use the Bernoulli equation. So it's going to go p3 plus 1/2 rho v3 squared plus rho g z3 is equal to p2 plus 1/2 rho v2 squared plus rho g z2. So one thing we want to recognize is that these points are in the free jet, and so the pressure here is atmospheric or 0 in this case, since we're going to be measuring a gauge, and these are just a pressure differential for which they're both atmospheric. So we're going to cross them out, ignore those because this is exposed to the atmosphere. The point is, we're going to assume it's barely seeing the atmosphere. Second of all, excuse me, we want to resolve the heights of these. So Z3, height of this, we can see it's 4 feet above the ground for the first faucet. So Z3 will be equal to 4 feet. And then Z2 is actually going to be negative 8 feet. We know that because it's 12 feet below the first one and 4 feet above the bottom floor because the floors are 12 feet tall. So the difference between that is 8 feet, and it is 8 feet below the ground, so it is negative 8 feet. So it will be gaining energy. It should be going quicker than 16 feet per second, it being V2 right here. All right, and with that, we are going to set up an expression for V2, which is, if we were to isolate for it, V2 would be equal to the square root of V3 squared plus 2g Z3 minus Z2. And we can just plug in our numbers here, where V3 is known to be 16 feet per second, quantity squared. We're gonna draw this a little closer to the bottom, where it will be 16 feet per second squared plus 2 times gravity. In this case, gravity is not 9.81. We are in feet, and so gravity is 32.2 feet per second squared, quantity times Z3 minus Z2, which is going to be 4 feet minus negative 8 feet. So that will turn into a positive, but we'll resolve that in just a moment. And then V2 is equal to this whole thing, where if we calculate this out, V2 is equal to 32.07 feet per second. So we're going to box this in gold because that is V2. So that's half of the problem. The second half is going to be V1, which is going up in altitude and thus should be slower than 16 feet per second. Notice how V2 is quicker because it went down, it gained energy, it transferred some of its potential energy into kinetic energy, thus increasing its velocity. V1 should be slower than 16 feet per second for the exact same logic, just going up in altitude. And with that, we will use the same expression where we will have P3 plus 1/2 rho V3 squared plus rho G Z3 is equal to P1 plus 1/2 rho V1 squared plus rho G Z1. Now in this case, Z3 is going to be the same. It is going to be 4 feet. Oh my goodness, that's a terrible F. Let's make this nice and neat. Feet. And Z1 is 12 feet above that, so it's going to be 16 feet because it's 1 story above. And you can kind of see right here, we've got the 4 feet and then the 12 feet directly on top of it. So V1 is equal to a similar expression to V2, where it will be the square root of V3 squared plus 2g Z3 minus Z1. So if we resolve that, V1 will be equal to let's move this down because this is always going to take up a little more space than I think. V1 is equal to 16 feet, well, feet per second quantity squared plus 2 times 32.2 feet per second squared. And then we will have 4 feet minus 16 feet. And all of that is square rooted. So if we resolve that, we get V1 is equal to 22.7 imaginary, which does not exist. So V1 is impossible. There is not enough energy for this flow to reach up to the second story because we can tell from the velocity coming out of the first story that it just cannot compensate. So we're going to box this. We're going to say V1 is impossible. There's not enough energy, and call it a day. Application problem 4. Find the water height HB in tank B shown in the figure below for steady state conditions. So for this, we are hunting down this parameter right here, HB, and this is tank B, this is tank A, and what we have given is a very weird situation where we want to balance it because it is steady state, where this will have the same mass in and the same mass out. So this is going to get interesting. And before we begin, there's a few things we should do. First of all, we should convert HA into meters. So HA is equal to 0.08 meters. Because everything else is in meters, we're going to be using gravity in meters. That's just going to be helpful. Second thing we want to do is we want to set the points that we're going to be using for the Bernoulli equation. The first point we're going to want to use is right here at the surface of tank A. Tank A has the most information given, so we're going to need to start here and work out to find HB. Second point we're going to want to put is probably right in the free stream here that's exiting tank A. That'll be point 2. And then the next point we're going to want to put is 3 here at the surface of tank B, and then 4 at the exit of tank B. So notably, we will be doing 2 Bernoulli equations, one going from point 1 to point 2. That is a free stream. We're allowed to do that. And then from point 3 to point 4. Notice how we're not going 2 to 3 because that would be using the velocity from 2. And as this water falls in here, it is not contributing to the bulk velocity of the fluid. That is important to note. Tank B is essentially a well, and if we start at the surface, we are assuming no velocity. This is important because we're assuming it's big. It's got these little flat lines. That is kind of a hint to say that this is a energy well, and so this velocity in from point 2 will not be contributing to the overall kinetic energy of the fluid here. So I want to get that out of the way in case you skip ahead. With that, we are going to start solving this. So we're going to go from point 1 to point 2 with the Bernoulli equation. So that'll be right here, 1 to 2. And we'll just jump right into it. P1 is equal, oh no, not equal to. P1 plus 1/2 rho V1 squared plus rho GZ1 is equal to P2 plus 1/2 rho V2 squared plus rho GZ2. Now, one thing we want to select is we want to set our datum for this equation here at point 2, so that way Z2 is equal to 0, which will cross all this out. And that'll make Z1 equal to HA. That'll be the most simple way to deal with this. Second of all, this is at P1, point 1 is at atmospheric, and so we're going to cross that out. That's 0. Point 2 is also at atmospheric pressure because it's in the free stream jet. So we don't need to worry about that. And it's also stagnant at the top. And so velocity 1 is 0, thus canceling this quantity out. So V2 is now equal to square root 2GHA. Very simple. And so we will plug in our values, 2 times 9.81 meters per second squared. Here, notice how we're using gravity in meters, and so we need to convert HA to meters. And so this quantity will be times 0.08 meters. This yields V2 as 1.25 meters per second. So with that, we then need to understand that we have a mass coming in, or a mass flow rate coming in, or volumetric flow rate coming in. Whatever, it needs to be balanced. This is in steady state. So volumetric flow rate going in is equal to volumetric flow rate going out. With that, we will take a look all the way over here, and we'll say Q, or the volumetric flow rate, is equal to V2 times A2, which is going to be very simple. That'll be 1.25 meters per second times pi over 4. This is the area equation, by the way, for right here, d1. And this is where I'm getting the diameter. 0.01 meters squared. This is 1/4 pi r squared. And that's just literally the area equation of a circle. So if you don't know that, unfortunately, you've got some big problems. 0.313 meters. No, I took a step too far. Ignore that. And this Q is equal to 9.84 times 10 to the negative 5. Holy crap, that looks like an 11. That is a times 10 to the negative 5 meters cubed per second. So that's perfect. That V2 came from right over here. We'll just make sure it's real obvious. And with this, we are going to solve for V4. So we will have Q, again, equal to V4 A4. And in this case, we have Q and A. So V4 is just straight up equal to, it will be Q over A4, which will not fit right there. So V4 is equal to 9.84 times 10 to the negative 5 meters cubed per second, all over pi over 4 times 0.02 meters squared. The 0.2 meters came from dB right here, and this yields 0.313 meters per second. You see where I got the 0.313. And with that, we will assess the Bernoulli equation. And so now we'll be going from 0.3 to 0.4. So 0.3 to 0.4. And it will be P3 plus 1/2 rho V3 squared plus rho G Z3 is equal to P4 plus 1/2 rho V4 squared plus rho G Z4. Now, there's a few things we can cancel out. First of all, the pressures, stagnant pressure is going to be 0 because this is atmospheric. At 0.3, there is no velocity, so this quantity will go to 0. We will set our datum at 0.4 equal to 0, so Z4 is equal to 0. And if we set Z4 equal to 0, that means Z3 has to be equal to HB, so that's very useful for us. And with that, we can solve for HB, and it is equal to V4 squared over 2G, which we can solve by 0.313 meters per second quantity squared, all over 2 times 9.81 meters per second squared, which gives us 0.005 meters. And HB, we're going to convert it back to centimeters because that's what HA was given in, and that'll be the most appropriate thing to do. 0.5 centimeters. So it's not very tall. So I don't want to hear your complaints about, oh, it's not like bulk velocity or whatever if it's flowing in and it's 1/2 centimeter tall, dude. Just that's how the problem was. And if you're given this on a test, just know if you don't have this height right here, then you probably are assuming that this is a well and you're not influencing its bulk velocity. Anyway, that's the answer. So I hope you enjoyed. Application problem 5. Water is siphoned from a tank as shown in the figure below. Determine the flow rate and the pressure at point A, a stagnation point. Before we begin, there's a few things we want to point out here. First of all, we have this triangle indicating atmospheric pressure at the surface of this well or tank. And then we have this symbol right here. This indicates diameter. So this 0.05 is a diameter, and notably it's the pipe diameter right here. So it's hard to tell what shape this is, what geometry this is. It is 0.05 meters in diameter. So now that that's out of the way, we want to point out where we will be putting our Bernoulli points. So we're going to do one here at the surface of the tank. And then we're going to do one in the free stream jet. So this will be 0.1, this will be 0.2, and we're going to resolve some of these. So the first thing we're going to do is we're going to solve for the flow rate. So we're going to go from 0.1 to 0.2. So we'll start over here, 1 to 2. And then we'll use the Bernoulli equation. So we have P1 plus 1/2 rho V1 squared plus rho G Z1 is equal to P2 plus 1/2 rho V2 squared plus rho G Z2. So first of all, the pressures are atmospheric, so that's going to be P2 is 0, P1 is 0. Then for 0.1, there is no velocity, so that kinetic energy term goes to 0. And then we're going to set our datum here at Z2. So the height of 0.1 is just 5. So Z1 is equal to 5 meters. And then we can solve for V2. So V2 is equal to square root of 2gz1. And that turns out to square root of 2 times 9.81 meters per second squared times 5 meters. And so V2 becomes 9.905 meters per second. We then want to find the flow rate, the volumetric flow rate. And so that will be Q is equal to V2 A2. And A2 here is just the diameter of the pipe. And so that will be 9.905 meters per second times pi over 4, 0.05 meters squared. So that's Q, and then Q is equal to 0.0194 meters cubed per second. So we're then going to box this, because this is one of our answers. That is the flow rate. And then we want to find the pressure at point A. So we will do solve for A. We'll do VA. Well, not VA. It is PA, where we'll find the pressure of A. So we're going to do that by Bernoulli equation. We're going to go from point 1 to point A. And so this will be 1 to A. So we'll have P1 plus 1/2 rho V1 squared plus rho GZ1 is equal to PA plus 1/2 rho VA squared plus rho GZA. So we're going to set our datum of height reference to the height of A, which will mean that is 0. And that means Z1 is equal to 5 meters. There is no velocity at a stagnation point. And so we're going to be solving for this PA. At point 1, there is no velocity. We have Z1 and the pressure is atmospheric. And so we just have this where PA uppercase is equal to rho G Z1. And that's 999 kilograms per meter cubed times 9.81 meters per second squared times 5 meters. So PA turns out to be 49 kilopascals. And that is the answer. So we have pressure of A and the flow rate of A.